Hey, my name's Casey, and I'm going to walk you through how to do LeetCode 907, sum of subarray minimums. So let's look at the input that they give us. They give us an array of 3, 1, 2, 4. And all they're doing here is they're breaking it up into all the subarrays that they can. So at first it's just the original subarray, then they take all the subarrays of length 3, then 2, then 1. Okay. And if we look at the minimum value in each of these subarrays, let's look at the minimum value here is 1. Now that the minimum value here is 1, 1, 2. So that's where these numbers are coming from, 1, 1, 2. And so they're just looking at all the minimum values in each of these subarrays, and they're adding it all up at the end to get 17, which is where they got their output from. Okay, so let's look at this example here that I typed out. So another way of thinking about this problem is how many subarrays is each value the minimum in those subarrays. So for example, let's say I ask you, this number 7 here, how many subarrays is that number 7 the minimum value in? And the way you check is you first look for your previous lesser element. So what's the first thing I find that before me that is less than 7? Well, that's this 4 here. So we do not want to include that 4 in our boundary, because if we did, 7 would no longer be the minimum value, right? 4 would be the minimum value. So we mark our boundary here, and then we do the same thing on the right. Where is our next lesser element? Well, it's not 16, it's not 12. 5 is the first element that we encounter that is less than 7, so we mark our boundary here. Now we don't even care about what's on the left and right. We just care about this guy right here in the center. How many different subarrays can I make? And this is one subarray, right? And this would be another subarray, the 16, 7, 10. And we could just keep mixing and matching these brackets, right? And this is another subarray with just one element of 7. Okay. So how many different ways can we mix and match these positions? These brackets on the left and the right. Well, there's 2 spots that we could put the bracket on the left and right. Here's one spot right here. This is 1. This is 2. So if there's 2 spots on the left, and there's 3, let's see, 1, 2, 3. There's 3 spots on the right that we could put the right bracket in. That just means that 7 is in 6 subarrays, where 7 is the minimum value. Okay, cool. And because 7 is in 6 subarrays, we want to count the number 7 6 times. Because remember, we want to find the minimum value in each subarray. So if 7 is in 6 subarrays where it is the minimum value, we need to count it 6 times. So that means if we were summing this up, we would do 6 times 7 equals 42. So this 6 just came from the subarrays, and the 7 is the value here. And we want to do this for every element. So for example, we want to do this for the 4, the 10, the 7, the 16, the 12, 5, 9. Okay, so let's just say we were going to do the 4. The first previous lesser element of 4, well, it doesn't have one, so we just go to the beginning of the array. And the next lesser element of 4, well, if you look at the array, there is nothing less than 4. So we just go all the way to the end of the array. And this would be, let's just do this one really quick. So there's 1 position on the left. How many positions are there on the right? It's 1, 2, 3, 4, 5, 6, 7. Okay, so there's 7 spots on the right. We can put our right boundary, which means there's 7 subarrays. That means we got to count the number 4 7 times. And that would give us 28. And we would end up, at the end, we would end up adding 28 plus 42 plus whatever value that we get from the 10, the 16, the 12, and all that. Okay, so now that we know what we're looking for, there is one corner case that I need to go over. And then we can start coding this out. Okay, so let's look at this little guy right here. In this array, what is the minimum value? It's clearly a 1. Well, remember earlier, what I just said is that we need to calculate how many subarrays each value is in, where it's the minimum value. The problem with that, though, is that this one is going to say, hey, I am the minimum value in this subarray of 151. And this one is also going to say the same thing. He's going to say, no, I'm the minimum value in this subarray of 151. So they're both going to say that they're the minimum value, and what would end up happening is we'd end up overcounting. So what we want is we only want one of these ones to count as the minimum value. We don't want both. Only one and any other one. So if we had multiple ones, let's say we had all these. Let's say we only want this guy or this guy to count as a minimum value, but we do not want the other three to count as a minimum value. And it doesn't matter which one we pick, we just need one to count and all the rest not to count as a minimum value in that subarray. So I'm going to explain how to do that with something called a monotonic stack. And monotonic stacks are perfect for finding your previous clusters and your next cluster elements, or a monotonically increasing stack is how you find your previous clusters and your next clusters. You would use a monotonically decreasing stack to find your previous greater elements and your next greater elements, but we're just going to do increasing for now. And if you want to know more about monotonic stacks, I'm going to go through an example of one really fast, but if you want to know more, I did a video on it like yesterday, so you can go watch that, and it's pretty detailed. So you probably should go watch it if you want to understand this problem. It's like a prereq, but I'm going to go through it anyway. Okay, so let's walk through an example of using a monotonically increasing stack to find our previous clusters and our next cluster elements. So in a monotonically increasing stack, all the elements are always increasing. So we're going to push this 4, and whatever is below me in the stack is my previous cluster element. So there is nothing below this 4. Therefore, there is no previous cluster element, which is why this boundary earlier that we put was to the beginning of the array. Now, if we want to push this 10, we can go ahead and do that. And now 4, because it's below the 10, is the previous cluster element of 10. And if we want to push this 7, we actually have to pop this 10 in order to push the 7, in order to keep our elements always increasing. Because if let's say we had 10 and we push the 7, this is no longer a monotonically increasing stack because 7 is less than 10 and we need our elements always increasing. So we have to first pop the 10, then we can push the 7. Now, 4 is the previous cluster of 7. And if we kept doing this all the way to the end of the array, where we pop everything that breaks our property of being an increasing stack, and then we just push, we would end up finding all of our previous clusters. And if we started from the end of the array, because right now notice that we're looping from the beginning of the array to find our previous clusters. Well, if we just started from the end of the array to push on the stack, start pushing on the stack, then that would find our next cluster elements. But there's a way that we could do this where we can loop through from the beginning and find the previous lesser elements and the next greater or equal elements, or vice versa. We could find the previous lesser or equal elements and just the strictly next lesser elements. Okay, so let me go through that really fast. So let's do it with the 151, because that'll make it clear why this works. So again, it's a monotonically increasing stack, so we're going to push this 1, and then we're going to push the 5, and that's fine. And all this is saying is the previous lesser element of 1 is nothing. There is no previous lesser. Cool. Previous lesser of 5 is 1. Sweet. Yeah, if we look at the array, the previous lesser of 5 is 1. Then when we want to push this 1, we're going to kick this 5 out, so we have to pop it because that would break our property. Now what I'm saying here is that because I popped you, so this 1 that I'm about to push onto the stack, if I pop you out, I am your next lesser element. So I'm going to go ahead and do that. Let's pop this 5. So I am 5's next lesser element because I popped it out. Now, here's the thing. We have these two 1s here, right? And I have a decision to make here. It doesn't really matter. It actually doesn't matter which one I choose. But here, I can either kick out this 1. And if I pop this 1, I am saying that I am your next lesser or equal element. Okay? Because if I pop the 5 out and I said I'm your next lesser or equal, and I also pop the 1 out because you're not less than me, then I am saying that I am your next lesser or equal element in order for this one to be down here. So I pop this guy and then I push this 1 onto here. The other decision we could have done was saying, well, let's just leave it here. We're not going to pop it out. Well, in that case, what I'm saying is that this 1 is my previous lesser or equal element. Okay, but because this didn't get popped, I'm saying that this number 1 here has no next lesser or equal element. Or sorry, has no next lesser element. So if we were to look at our boundaries here, the boundaries for this 1 here would be, assuming that if I just leave the 1 in here. So this would be my left boundary. This would be my right boundary. Because again, I'm saying because I didn't get popped by any, if I got popped by nothing, I have no next lesser element. Okay. And the boundaries for this one right here, I'm saying that this 1 is my previous lesser or equal. So its boundary would actually be here. And that is exactly what we want, because we only wanted one of the 1s to count towards this subarray. And that would be this one that we did earlier, a second ago. So that is how we're going to loop through our monotonically increasing stack. Or we just mark we're just going to store our next greater or equal elements, and we'll just store our strictly previous lesser elements. Or we could do it the other way around, but it doesn't matter as long as one of them has the equal element and one of them doesn't. Okay. So let's actually code this out. So we can just go ahead and create our stack. Let me actually clean up all this empty space. So we're going to have a stack of indexes in the array. And we want to loop through our array because we want to push all of these elements onto our stack to find our previous lessers and stuff. So r.length ++ I. And now this is where we want to... So before we push onto our stack, we need to pop everything that breaks the increasing stack property. So we're going to do a while loop. So while stack is not empty, and stack.peak. So what I'm doing is I'm just checking whatever the top element is to compare it to what I'm about to push. And I said I was going to store the index. So stack of integers, this is going to be the indexes, not the actual values. This is the indexes in the array. So I'm going to peek at the index, and I know this is okay because I checked if it was empty. So I'm going to check what the value is here in the array, and I'm going to check. So because it's an increasing stack, whatever is below me, it cannot be greater than me, greater or equal. Yeah, so if it's greater or equal to me, that would break our increasing stack property. So if this element, so if this element is less than whatever I'm about to push it onto, we need to kick this out. So let's go ahead and do that. Stack.pop. And we're not quite done here. So remember what I said earlier is if we pop it out, I am that element's next lesser element. So this I, or this value here, because I'm popping this out, I am that index's next lesser value. So I actually need to create some arrays to store these previous lesser and next lesser values. So let's do that really fast. Int previous lesser equals new int length. And we're going to do our next lesser, or equal, just to be explicit, so that's very clear what we're doing. So this is going to hold all of our next lessers and our previous lessers, and this is actually, well, next lesser or equals, right? Okay. So let's, now remember what I said, if this element right here is popping this guy, that means that this I, or this value, is going to be this index's next lesser value. So let's do that, next lesser or equal equals I. And I'm just storing the index here. Okay. Is this good? We need to, so now we need to do our previous lesser. So now that we assume that this just popped everything that broke our property, and now we need to check what is underneath me, or what is about to be underneath me when I push myself onto the stack. So whatever is on top, so we want to do stack.peak, but in this case, there could be nothing underneath me, right? Because, yeah, if we popped everything in the stack, if there's nothing underneath me, that means I have no previous lesser element. So we want to first check if the stack is empty. If it's empty, well, then we have no previous lesser element. And if it's not empty, well, then we just take whatever's on top. Or, yeah. And that is my previous lesser. And then finally, we want to push our index onto the stack. So we're pushing everything, and we're pushing every element into the stack. And we're just going to do this, and we just do this for every element. So that took care of finding our previous lessers and our next lesser are equals. And now all we need to do is calculate the left times the right and multiply that by the value in the array, because that would be the minimum value in that many subarrays. And we just sum that up. So let's just create a sum variable. And there's one little quirk in this problem where the sum, okay, so this sum could get like super big and there could be stack overflow or whatever. So they want us to mod our sum by this value. So the way we do that, we just do double mod equals 1e9 plus 7. If you haven't seen this before, this is just 1 times 10 raised to the 9th plus 7. Okay, and I'll leave that there. So let's sum up all of those left and right boundaries or whatever. So left for int I equals 0, I is less than r dot length plus I. And we need to create those left variables. So let's just say int left, int right. And then we're going to say sum. This is just, I'm going to type out this in a second. I'm just typing out some template code. So sum plus equals the left times the right. So this would be the number of subarrays, right? This is the number of subarrays, and we need to multiply it by that value. So this is the number of subarrays times how many subarrays this minimum value is in. Or sorry, let me just say that one more time. If this was our 7 up here, remember this was our 7. And we said earlier that this 7 was in 2 times 3 subarrays. This would be the 2 times 3 subarrays. Okay, so that's all that is right there. So we summed it up, and then they want us to mod it because it could get really big. So mod equals, or sorry, sum mod equals mod, which is just this guy up here. And at the end, we want to return our sum. And that'll give us the right answer, assuming we could type out 2 more lines of code. So we just need to figure out what the left and right boundaries are. And that's super easy because we figured out what our boundaries were earlier. So we just, for the left, we just do whatever my current index is minus the previous lesser I. And, oh. Okay, I'm going to go back. I've missed one line of code up here, and I know it, and I'm going to go over it in a second. But let me keep going, and I'll explain what that line of code is. Next, so for the right, it's our next lesser or equal. Yeah, next lesser or equal minus I. Okay. So it's better if I go through a really quick example to explain, to make sure, to confirm to you guys that this does indeed work. And then you'll see what code I need to add up here, or what line I need to add up here. All right, let's just take our original example because we'll just stick with that. And I feel like it's already in your guys' heads. Why explain another example? So this 7 up here, let's say the 7. This is index 2. So this I is 2. My previous lesser, in this case, is 4. And what I'm saying here is 2 minus 0 equals 2. Well, in this case, 2 equals 2. Oh my gosh, I can't type. 2 equals 2 minus 0. Okay, we can see that that works. And because there are two positions to the left, right? Let's remove these brackets so it's not confusing. There's 2 spots that we can put this bracket in on the left. There's one there, one there. Cool. And then let's just say that this happens to be, let's say we're on I equals 0. If I was actually equal to 0 right now, then let's get rid of this, get rid of that. So I is equal to 0. We said up here, if there is no previous lesser, then we're going to set it to -1. So our previous lesser in this case would be -1. And 0 minus -1 is 1. Because minus plus, okay, we all know how to do math. So left would equal 1, and there is indeed one spot on the left of that 4. Okay, so this line of code is definitely correct. Now, the line of code that I messed up, or that I forgot to add, let's just do the right and you'll see what it is. So let's take this, let's see, which value do I want to do? Let me shorten this down a bit so the math is just super simple. Let's say there was a 2 here. So we'll start with the basic example. Let's bring this down. Let's say we're doing the 7 again, right? This is index 2 again. And our next lesser would be at index 4. So 4, this would be a 4 here. Minus 2 is 2. And are there 2 brackets to the right? 1, 2. It is. So we know for the basic case it works. Now, where I know it fails is let's take let's say there was no previous or next lesser elements. Let's remove that too. Let's say this is all we have to work with right here. Well, because I have no next lesser element, right now I would be saying next lesser or equal. So this would be equal to 2 minus 0, and which is wrong. Wait. Sorry, no. 0 minus, this would be 0 minus 2. So this I is this 2 up here. And the reason this is wrong is because we get -2, right? There isn't -2 spots to our right. And that's because, an integer array, it'll just initialize all the values to 0 at the beginning. What I needed to add is, let me just copy paste this. I need to initialize all the elements in the beginning to r.length. Because remember, if an element doesn't get popped, it has no next lesser element. So if it's not going to get popped, what ends up happening is it'll just stay as this value. That index will just stay as r.length. And yeah, and if it was going to get popped, it would just get over in here by the actual next lesser value, or the next lesser index that it's at. Okay. So now what I'm saying here, because I just took care of this line, now what I'm actually saying is the next lesser or equal is no longer 0, because I filled it with r.length, which in this case, there's only 4 elements here. That would be 4 minus 2, because of this 7 is at index 2. And there are 2 spots to the right, and 4 minus 2 is 2, so now I know this is correct. Okay, and I'm super sorry I forgot this line. I should have included it, but hopefully that makes sense. If it doesn't get popped, it has no next lesser, and this value will never get overwritten because, yeah, it just won't. Okay. So yeah, let's go ahead and run this, make sure it's all right, and I think we're done. So let's see. Of course, I made a mistake. I forgot to cast this back. And I made this so long because I didn't want to deal with Stack Overflow. Or did I go wrong? Did I make a compile error? Or did I mess up? Let's see. RI times left times right, some mod. This looks fine to me. Did I mess up the mod? Is that what this is about? I think I did. Let's see. Long sum equals 0, double mod. I'm gonna change these to longs because I think I just have Stack Overflow. Let's try that again. Oh, that was what it was. Okay, cool. So yeah, I can just guess these, the I minus and the next, whatever subtraction, addition, whatever I'm doing here. It just had some Stack Overflow. So anyway, yeah, so that's how I would solve this problem. There is an alternative to finding the previous cluster and next clusters if you don't like how I did it. So like, for example, 'cause I did this in one loop, right? There's another way to find these previous clusters, which I hinted at earlier, where if I loop from the beginning of the array, I can find my previous cluster elements. And if I loop from the end of the array backwards, I can find my next cluster elements. But if you want to try to do it that way, it's totally up to you. Maybe go watch my monotonic stack video to see what I mean by like looping from the back and looping from the front to find your next clusters and previous clusters, whatever. But yeah, that is it for this problem. And oh, I guess time complexity. So when you use a monotonically decreasing stack or increasing stack, whatever, the time complexity is just O of n to find all the previous clusters and next clusters, because each element in the array that we're pushing and popping every element gets pushed once, but every element only gets popped at most once. So that's just like at most 2 operations per element in the input array. So the time complexity is just O of n. And yeah, so you can clearly see we just do one loop here, so that's still O of n, and this fill is O of n. So the whole time complexity of this whole entire thing is just O of n. For space, you would just say it's O of n because of the stack. And these arrays that we create here are just O of n. Okay, so yeah, that's it. Thanks for watching. If you liked the video, if it helped at all, you can like the video. And you can subscribe if you want to see more videos, and just comment below if you want to see any other problems. Okay, bye.